Hello, in this video we're going to look at using the chain rule with trig functions. So in other words, we're going to look at trig functions that are more than just the basic ones that we looked at in the previous video. So I'm thinking about these sorts of functions. Let's get a blue pen. I'm talking about y is equal to 2 sine x, or I might be talking about y is equal to sine of 2x, or I might be talking about might be talking about y is equal to sine of 2x plus 1, or even something like y is equal to the sine of x squared. Now basically we've got some composite functions happening here, and so we need to think about how that's going to affect the graph and what it looks like. As usual, I'm going to go and play around with GeoGebra and have a look at these. So here we have the basic sine function. I want to see what the derivative of 2 sine x is going to look like. So I go to my function over here and I go and put a multiply by 2 there. And there's our graph of y is equal to 2 sine x. It's got an amplitude now of 2, it goes up to 2, but the period is still 360 degrees. Now, what are we going to expect the derivative of this to look like? Well, I'm anticipating that I'm going to be using a cos function, because that was what the derivative of sine was. And as I move this along, we'll see the other graph appearing alongside it in black. And as that runs through along the curve, and we see the gradient of all those points along the curve, we can see that we've got a fairly familiar graph. It's not the cos graph, that's the cos graph down there, but if I go and multiply it by 2, you'll see there that it fits exactly onto the plotted points there. And so we've got the first of our derivatives. Go back to the notes. So if we look at the derivative of y is equal to 2 sine x. So if we go and look at the derivative of 2 sine x dx, that's going to come up as 2 cos x. Which I suppose is not too surprising. We're expecting that the sine graph is going to become a cos graph. So that's possibly anticipated. Now we need to think about what's going to happen with sine 2x. Now we need to realize this is a composite function. There are two things happening here. X is being doubled, and then x is also going to be affected by the sine function. So this is why we have to use the sine rule. And not the sine rule, the chain rule, to look at this. So let's go and see what this looks like in terms of the graphs. So here is the graph of y equals sine 2x. The amplitude is just 1. The coefficient in front of the sine function is 1. However, the period of the graph is now going to be 180 degrees. I'm going to get 2 complete waves within 360 degrees, or within 2 pi. So they're my 2 complete waves. Now, when we go and run the point along and see what's happening with our derivatives, firstly you'll notice the first derivative point is starting up over here at positive 2. So as I move this along, it's dropping down, and as I complete my first full cycle, I can see that I've created a cos graph, but it's got an amplitude now of 2. Keep that going on, go through our full 360 degrees. You can see that we've got 2 of these curves, so the derivative is also going to have a period of 180 degrees. So it's not simply the 2 sine graph, the 2 cos graph, the derivative, we're going to have to go in here and amend this. It's going to be 2 cos 2x, and there is our derivative. So we can see that the derivative of sine 2x is going to be 2 cos 2x. From the diagram then we have this. We have the derivative of sine 2x dx is going to be 2 cos of 2x. Now we need to use the chain rule to help our understanding of why this is the case. So if I take my original function, y is equal to sine 2x, sorry, and I say let 2x equal a, then my original function is going to look like this. It's going to be y is going to be sine of a, and I can go and take the derivative of a. I can go and take the derivative of a with respect to x, and that's going to just give me 2. The derivative of 2x is just 2. I can also go and look at the derivative of y in terms of a, and that's going to give me cos of a. So if we try and join these two together now, so if we go and say what is the derivative of sine 2x dx, well, it's going to be the derivative of y with respect to a times by the derivative of a with respect to x. That's the chain rule. And so I'm going to get cos a times by 2. And in fact we know that that a is equal to 2x, so it's simply going to be cos of 2x, 2 cos of 2x. And so there's our derivative of this. So the next option or next function that we looked at was this one, y is equal to sine of 2x plus 1. Well, if we go and take a look at the graph of this, we'll see what we can get. I just need to tidy this up. So this is what we've got now. We've got y is equal to the sine of 2x plus 1. Now we know from the work that we've done with transformation of graphs, this 2x plus 1 is going to shift the graph basically 1 over to the left. Remember, we're working with radians here along the x-axis. So it's shifted the sine graph to the left. But otherwise, the function should operate much the same. So let's see what happens when we move these points along here. We're still getting the derivative going down to a minimum of -2 and up to a maximum of +1. We've still got it doing 2 waves within 360 degrees. So in other words, within its period, it's covering the same space as it was before. And if we take this all the way back to the start and find where the graph is when it's at its maximum, we'll see that we've got basically a cos graph again. It's got a period of 180, so it has to be a 2x graph. And it's got an amplitude of 2. It's going up there. Now if we go and look at what that graph looks like, that doesn't match up. In fact, what we've got to do is we've got to go back into here and go and add 1 onto that, so that the graphs will match up. And there we have it. So the derivative of y is equal to sine 2x plus 1 is y is equal to 2 cos 2x plus 1. And if we go back to why this is, we look at the chain rule. Once again, we're going to say let 2x plus 1, not plus a, 2x plus 1 equal a. So in other words, my function now looks like this. Y is equal to sine of a. Here I can say that the derivative of a with respect to x is going to be 2. And I can say that the derivative of y with respect to a is going to be cos a. And so, if I now look at the derivative of the sine of 2x plus 1 over dx, this is going to be dy dA times by dA dx. This is going to be cos of A times by 2. In other words, it's going to be 2 cos, the value of A was 2x plus 1. So we're using the chain rule once again. We basically are deriving what's inside that bracket. That goes in front of the ratio, and then we keep the angle the same. The last of the graphs that we were looking at was y is equal to sine x squared. Now, I'm just going to go straight into the chain rule basically. I'm going to say let x squared equal a. I know then that dA dx is going to give me 2x. I know that my function now reads y is equal to sine A, and so therefore dy dA is going to be cos of A. And so using my chain rule I can say the derivative of the sine of x squared with respect to x is going to be dy dA times by dA dx. This was cos A, and this was going to be 2x. In other words, my full derivative is going to be 2x cos of x squared. So that's what we're anticipating it should be. Let's go and see if that's what actually happens when we go and graph this. It's going to be an interesting graph to look at. Right, there's the function. Let me just tidy up first of all. Right, so first thing, let me say that the graph is going to look really strange. Here it is. This is the graph of y is equal to sine x squared, not something that we normally see. And we reckon that the derivative was going to look something like this one over here, the one we've got in red. If we just go and run the point along this curve and see what happens to our gradients. So it looks slightly unusual there. Oh, it's going down way down here. It's going way up top there. It's coming down. So basically, hard to see where these points are going to be as we run through it. By the way, if you can hear a funny background noise, it's just the washing machine going. Just been aware of that, suddenly aware of it now. So these points seem to be fairly random all over the place. Coming back through, and here we are. And it seems to map out on the other side. Let's go and see what if this actually matches up with the derivative that we think it is. And there we can see, yes, it does. It fits exactly onto it. If I have to scroll out, we'll see the graph really does some strange sort of things. Now, fortunately, we're not expected to know what those graphs look like, but it is quite unusual seeing the derivatives of these things. Obviously affected by the fact that we've got an x squared and the fact that we're then going to be looking at 2x times by this cos x squared graph. That's what makes the whole thing look peculiar. So, hope that helps. We basically looked at using the chain rule on trig functions. Goodbye.